Hi everyone. Today we will discuss about single source shortest path algorithm, simply called as SSP. The algorithm name is Bellman Ford. Okay. Single source shortest path, it finds the shortest path from one source vertex to all other vertices in a graph. In Bellman Ford is a simple shortest path algorithm used to find the minimum distance from source to all other vertices in a weighted graph. It can handle negative 8 weight also. Okay, what is 8? Weight means vertex. So this is one vertex. This is another one vertex. 2. So connected with one edge. Okay. So some weights are there. So this weight is in negative value. So that is called a negative edge weight. Okay. This is weight. Okay. Some value is present here. So this is called a distance. This is called a distance. Okay. Some values there means this is called a distance. This is called weight or cost. Clear? Okay. It follows dynamic programming strategy because it builds the final shortest path solution using previously computed smaller solutions. Okay, so that is called dynamic programming, and we find out all the possible solutions, then pick up the best solution from the all the possible solutions. That is also dynamic programming concept. So basic idea here, relax all edges repeatedly. That is very important concept in Bellman Ford, that is relaxation. So repeat for v minus 1 times. V is the number of vertices. What is relaxation? So updating shorter distance if a better path is found, that is called a relaxation. Okay. So we examine its own formula is there. If distance of u, very simple formula, distance of u plus weight less than distance v, not u here, distance v, right? U and v is the two adjacent vertex. Imagine like here u is there. This is v, 2 is the two adjacent vertex connected with one edges. Connected with one edge, clear? So some distance is there. So distance of u is just assume the distance of the vertex u is 2, right? So distance of v is 6. Here some value is there, that is weight. Here we write the weight also, weight is 3. So weight of the particular path is 3. Weight or cost. Okay, what is the formula? Distance of u plus weight. That means you find one new value. Simply add this distance with this weight. Okay, what is the answer? 2 plus 3. Add 2 with 3. The answer is 5, right? Answer is 5. Then compare this value, this added value with this value. Vertex v distance. Which one is small? So 5 is smaller than 6, right? Then we update the distance like 5. Okay, which one is small, you updated with that value. So that is called a relaxation. Clear? Okay. So then update distance of u with that smallest one, smallest value. So that is called a relaxation. So algorithm of Bellman Ford, initialize source distances 0, set all other distances infinity. Relax all edges v minus 1 times, check for negative weight cycle, then stop. So Bellman Ford algorithm is used to find the negative weight cycle also. What is negative weight cycle? So the path starts from one vertex. Okay, start from one vertex. The path reach the same vertex, that is called cycle. Okay, that is called cycle. What is negative weight cycle? The total of this path is in negative weight. So the total of all the weight in the graph is the some negative value. So that is called negative weight cycle. So how to find the negative weight cycle in Bellman Ford algorithm means we already know that we perform the relaxation, right, to update the minimum distance. So we we enough to perform v minus 1 relaxation to find the result. Clear? If the vertex contain, sorry, if the graph contain 5 vertices, we need only 5 minus 1, 4 times relaxation to get the final result. But after v minus 1 times, still some updation is there in the graph, means the graph contain negative weight cycle. Okay, likewise we find the negative weight cycle in the Bellman Ford graph. Clear? Okay. Take this as one example. What are the edges are there? 1 to 2, 1 to 3, 1 to 4, 2 to 3. Then so we write in the order, that is must. Okay. So you calculate the vertex, the edges for 1 to connected vertex. Vertex 1 to all the connected vertices. 1 to 2, 1 to 3, 1 to 4. And perform the relaxation in 2 to 5, then 3 to 5, 3 to 2, then only perform 4 to 3, 4 to 6, 5 to 7, 6 to 7. This order is very important. Okay, we relax the edges one by one. First start with the vertex Z1, 1 to all other vertices, then 2 to all other connected vertices, then 3 to all other connected vertices, and 4 to. Likewise, you perform the relaxation one by one. So, initially, what is the first step here? Source distance as 0 and all other distances infinity, correct? So, initially we take this like, so source vertex as 0, all other vertices is like infinity, all other vertices is infinity, clear? Okay. Then how will update the weight, distance, that means relaxation, how will perform the relaxation? So, in relaxation 1, we know the simple formula, right? So, perform 1 to 2, 1 to 3, 1 to 4 initially. So, in 1 to 2, what is the distance here? That is the distance 0. What is the weight here? 6. So, simply add these two things. What is the value? 0 plus 6, that is 6, right? 6. What is the distance of this adjacent vertex? The distance is infinitive initially, right? So, 6 is less than infinitive. So, update with this value. Okay, now the newest distance is 6 because 6 is less than infinity. Clear? Then move to this edge 1 to 3. The order is very important. We perform 1 to 2 is over, right? 1 to 2 is over. Then perform 1 to 3. So here 0. Here what is the value? That is 5, right? So 0 plus 5, 5. 5 is less than infinity here, right? So update with 5. Clear? Then, so this edge is over. Then here 1 to 4, the value is 0. Here the distance is 5, weight is 5. So distance plus weight, 0 plus 5, the newest value is 5, right? The newest value is 5. 5 is less than infinity, so update it. So the newest distance is 5 here. Okay, 0 to 4 over. So carefully listen the concept. Then next, so all the adjacent vertices from source vertex, from 1 is over, then start with 2. Then 2 to what are the 2 only connected with the adjacent vertex 5. Okay, then perform the relaxation on this edge. So 2 to 5, already this updated, the value is 6, right? So now consider the newest value. No need to consider the previous infinity value. Now consider the 6. Value 6. So 6 plus 1, what is the value? That is 5. Right? 5. So 5 is less than infinity. So update it with the new value 5. So because 5 is minimum than lesser than infinity, right? Then 2 to 5 over. Then perform then relaxation. Relax the path from 3 to all other adjacent vertex. So 2 edges are there, 3 to 2 and 3 to 5. Then perform 3 to 2 and 3 to 5. Okay. Then 3 to 2. Here what is this? This is 5, right? So 5 minus 2, what is the answer? So 5 minus 2, so that is 3. 3 is less than 6, right? So update here 6 with 3 here. Clear? Now the newest distance is 3. Then 3 to 2 over, right? 3 to 2 over, then 3 to 5. So here is 5, here 1. So 5 plus 1, what is the value? That is 6, right? But already here the value, the distance of 5 is 5. So 5 is smaller than 6, so no need to update because already the 5 is the smallest one. Then the newly calculated value. So no need to update here. No updation is there. So 3, 5 completed, but no updations will perform. We keep the previous value. Then 4 to 3. So what is 4 to 3? Here what is the value of 5? Here minus 2. 5 minus 2, that is 3, right? So 3 is less than 6. So here updated with 5 minus 2 less than 5, right? So updated with 3. Newest value 3 is minimum one. Clear? Then 4 to 3 over. Then perform 4 to 6. So 4 to 6 here 5. 5 minus 1 4. So 4 is less than infinitive. Then update with the new value. Okay, 4 to 6 over. Then 5 to 7. 5 to 7. Here is 5. 5 plus 3, that is 8. So 5 plus 3, 8. So 8 is less than infinitive. So update here 8. Okay, 5 to 7 over. Then 6 to 7. What is the value? So here 4, here plus 3. 4 plus 3 is 7, right? So 7 is less than 8. The updated. Sorry. So which one is minimum? Update that value. Okay. 7. Clear? This is called relaxation. Now first relaxation is over. Yes, we update the distance for all the connected edges. Clear? This is relaxation 1. Likewise, you perform the relaxation 2 also. So the newest. Okay, this is the newest graph. Okay, all the updaters. So here 3 plus 1 4 5 minus 1 4. So this is the updated one. Okay, clear? Likewise, you update all the edges one by one. So relaxation 1 is over and you perform the relaxation 2 based on the same procedure. Okay, clear? Right. Then find the next relaxation 2 will perform the relaxation 2 and perform the relaxation 3. Likewise, you perform all the relaxations. Okay. Then finally, after V minus 1 time, so no need to perform relaxation because before the V minus 1 time, we get the final result. No updation is there. That is the final result. In some cases, after 3 or 4 relaxation tips, we get the final result. So no updation is there means that is the final answer. Okay. So we'll discuss, explain the one more concept. This is very simple graph, right? So what are the edges are there? 0 to 1, 1 to 2, 1 to 3, 2 to 4, 4 to 3. This is present in the edges table. Okay, here source vertex is 0. So these are the weight. Then in step 1, that is initialize. Set distance of sources 0. All other vertices are infinite. We know that, right? Then maintain the values maintained in one table. So what is the rule here? Relax all edges in V minus 1 times. So here 5 vertices are there. So how many relaxation? Here the relaxation means iteration. So iteration is represented for the relaxation in the edges. Okay. So we need a 4 iteration here. In iteration 1, first we take the edge 0 to 1. Then perform the relaxation. So update the minimum distance in the adjacent vertex. Clear? So maintain the separate array will use to maintain the updated distance. Okay. Then 1 to 3. Then perform 1 to 2. Then 1 to 3. Then 2 to 4. Then 3 to. So no edges from 3 to 4. Then skip that vertex. Then 4 to 3. Like you say, one by order you relax the distance in the given graph. Okay. This is iteration 2, but here no updation in the iteration. So after in this graph, only one iteration is enough, because in further iterations no updation is there. In iteration 2 no updation, so this is the final result, and no need to perform iteration 3 iteration 4 again and again, because no updation, already the updation is no more updation is there. Then we consider this is the final result. Okay, so actual concept is we need v minus 1 relaxation, but in not at all cases we should perform v minus 1 times. So no need. Okay, if some relaxation step have no changes in the given graph means just stop the process. That is the final answer. Okay, then write the final shortest distance in the table. From vertex 0, what is the distance? Final distance 0, 5, 6, 6, 7. Then final shortest path from source to. So this Bellman Ford algorithm is used to find the shortest path from source to all other vertices, right? So from 0 to all other vertices, 0 to 1, 0 to 2, 0 to 3, 0 to 4 through the intermediate vertex. So which one is smallest one, we write it. We choose that path. Clear? So on destination 1, so 0 to 1 the cost is 5, 0 to 1, 1 to 2 the cost is 6, 0 to 1, 1 to 2, 2 to 4, 2 4 to 3 the cost is 6, right? So many possibilities are there to reach 0 to 3, but we choose this path because this is on the shortest distance. Clear? This is the shortest distance. So here vertex 0 is 0, 0 to 1 we take only 5, cast the weight is 5, then 0 to 2 6, 0 to 3 6, 0 to 4 7, we formed already find the shortest distance, right? That is cast. Then just here just find out the path 0 to 1, 0 to 1 to, what is the path? Give the cast value 6. Okay, then likewise we form the path also. This is the final updated result. So important point is here Bellman Ford works with negative weight also, can handle negative weights. Okay, and here the 4 to 3 the weight is minus 1, right? This is in given graph. So no negative cycle exists in this graph. That is very important. If any negative cycle is in this graph, we cannot find the result using Bellman Ford algorithm, because here here 1 to 2, so no cycle performed because the direction is reverse 4 to 3. Okay, if the path start from 1 and again reach to the 1 means this is cycle. This is called cycle. This is not allowed in Bellman Ford. So negative cycle check. How to find the negative cycle using Bellman Ford algorithm means, after we know that after v minus 1 iteration we find the result, right? Before v minus 1 iteration or after v minus 1 iteration we find the result, sure, using Bellman. But after v minus 1 iteration do one more v minus 1 iteration is enough to find the solution in using Bellman Ford algorithm. Okay, so we need one more iteration. After v minus 1 iteration, if any distance can still be updated in the given graph means, then the graph we finalize the graph contain negative cycle. Clear? Okay, no distance gets updated here, so no negative cycles is there. Here we get the answer in one relaxation. Okay. Okay, so time complexity is order of V into E, vertices into edges. Clear? So this is concept of Bellman Ford algorithm. Thank you.